So here's a question for you. What happens when electricity completely loses its brakes? It's kind of an extreme what-if scenario, I know. We usually only think about how to get electricity flowing in the first place. But keeping that flow safe and controlled, that is absolutely crucial. To understand how our everyday devices don't just, instantly burst into flames the second we turn them on, we really have to understand those brakes.
Part 1. Let's meet volts, amp, and ohm.
To really wrap our heads around this, let's introduce the three core forces of electricity, not as abstract math equations, but as characters in a very real, very physical struggle. Picture this incredible dynamic. You have Volt, right? He's the big guy forcefully pushing from behind, providing all the pressure. Then, right in the middle, getting completely squeezed and shoved, you have Amp. Amp represents the actual current, the flow of electricity, just trying to make its way through the circuit. But then, acting as the ultimate counterforce, you have this muscular character named Ohm. An ohm is desperately pulling back on a rope, tightening the space Amp has to move through, and just fighting against Volt's relentless push.
The big takeaway here is that ohm represents resistance. Just as he physically opposes the push of volt and restricts amp, electrical resistance is the property that literally opposes the flow of current. Ohm is the necessary set of brakes keeping the flow of amps totally in check. Without him constantly pulling back on that rope, the entire system would completely lose its balance.
Moving on to part 2, the water pipe analogy.
Let's ground this in a really relatable analogy so we can visualize it in our day-to-day world. If you've ever used a garden hose, this dynamic is going to make perfect sense. Think of voltage, our character Volt, as the water pressure pushing right from the source. It is the driving force. Then think of current, or amp, as the actual volume of water flowing out of the hose. And finally, we have resistance, which is ohm. In our water analogy, resistance acts like a narrow section or a physical kink in that pipe. It creates a bottleneck. And no matter how insanely high the water pressure gets, that narrow section is always going to control and limit the rushing flow of the water. Section 3. Let's look at the math of electricity. Okay, now that we have our mental model firmly in place, the push, the flow, and the bottleneck, let's see how Ohm's law mathematically quantifies this exact relationship. Don't let the letters intimidate you here. It's actually beautifully simple. V equals I times R. Or, if we flip it around to see exactly how flow is determined, current equals voltage divided by resistance. This math shows us exactly how our three characters interact. It basically tells us that if you know how hard Volt is pushing, and you know how hard Ohm is resisting, you can calculate the exact flow of the current, the amp. They are forever locked in this perfect mathematical balancing act. Just notice how dramatically this scales in reality. Let's say we have a standard 12-volt battery. If Ohm is pulling with a resistance of 12 ohms, the current is a very calm, totally manageable 1 amp. But if we keep the voltage exactly the same at 12 volts and just drop the resistance down to 1 ohm, the current absolutely skyrockets to 12 amps. Literally, by just easing up on the brakes a tiny bit, the flow of electricity multiplies 12-fold. Which brings us to part 4, when resistance disappears. So let's escalate this and ask the ultimate what if. What happens if Ohm just decides to let go of the rope completely? Well, this is where things get serious. If that resistance drops to 0, if Ohm totally disappears from the equation, while the voltage stays exactly the same, the mass completely breaks down in a terrifying way. The current doesn't just gradually increase, it immediately explodes into a massive, completely uncontrolled surge of electricity. The brakes are literally gone.
Part 5. The destructive short circuit.
This sudden, massive rush of power brings us to the very real-world consequences of a circuit functioning without resistance. Going back to our water analogy, imagine if that narrow kink in a highly pressurized pipe suddenly just vanished. The water would blast through with incredible violent force. In electricity, this terrifying event is what we call a short circuit. It is exactly what it sounds like. The electricity has somehow found a shorter, easier path with zero resistance, completely bypassing the components that were supposed to safely slow it down. And the fallout of a short circuit is disastrous and immediate. The wires, which are now acting as a wide-open superhighway for all that unresisted current, can rapidly overheat. The delicate little components inside your devices, they'll burn out instantly. Any batteries connected to the circuit will discharge their energy incredibly quickly, which is highly volatile. Now, if you're lucky, your fuses or circuit breakers will recognize this massive surge and trip, physically breaking the connection.